our SN1s. Any questions about what's up here right now? This is what we talked about on Monday. Hopefully you're all fairly confident with it-ish. Okay. We talked about the substrate structure. So when we look at the SN1 reaction, the primary thing that you are concerned about is what is happening in that very first step. That's it. Okay? So within that first step, all we really care about is our substrate. Okay? So there's no nucleophile, nothing else. We don't have to worry about it. The other aspect that we could look at is the stability of the products, because for that first step to occur, our products have to be relatively stable. Okay? Leaving group is going to come off regardless in all situations, so really that's just deciding what atom is the best leaving group. So again, not particularly helpful. Our big difference is going to be that carbocation. That carbon has to be able to stabilize that positive charge. So when we're looking at the SN1 mechanism, we want to deal with substrates that can stabilize that carbocation as best as possible. And when we've talked about mass spec, we talked about different carbocation stabilities. That's how mass spec actually functioned, was looking at carbocations. And we went through and said that our tertiary carbocation is the most stable, and our zeroary or methyl group or methyl cation is the least stable. Okay? So our tertiary is labeled at the bottom. Come on now. We've got our tertiary down here. Now what I like to call is the zeroary. There's no carbons attached. Okay? So when we're looking at the SN1 mechanism, we really want a stable carbocation. If we have that stable carbocation, we do predict a reaction. With that caveat, it's not just primary, secondary, tertiary. There's other things that can contribute to overall stability of a carbocation. So what we've got on the far right are a couple different examples that we could look at. All right, for that very first one, how would we classify that halide? Usually gets referred to as primary, because when we look at the carbon to which our halogen is attached, it is attached to only one other carbon, which means we have a primary halide. Okay? Those of you in lab might help classify this. Would we expect a primary halide to react in an SN1 reaction? No, because we form one of our really, really unstable carbocations. Okay? However, this species does react. Okay? We do see a reaction in this. What does that necessarily mean? That carbocation, or the carbocation that is formed in this, must be stable. There is no other option. Okay? So if we drew that out, hopefully what you would see is that we have a resonance stabilization, and what we can do is displace that positive charge by shifting the electrons around and putting it on a different carbon. Yes, that different carbon is a primary carbon as well. That is kind of secondary to the point of this. The initial structure that we drew, what we're concerned about is the stability of the carbocation on that atom. So when we now look at resonance, we can't say just that atom is our answer. We have to look at both these structures. So we would look at the charge in both of those structures on that carbon atom. In one case it's positive, in the other case it's neutral. So the average charge on that carbon is less than positive 1. Comes out as a positive half if you really wanted to get numerical with it. What does that mean happens to the stability of that carbocation? It becomes much more stable. If we have a stable carbocation, the SN1 reaction can work. We see the same result when we look at the very last one. Okay, the very last one gives us that same kind of primary issue again. Because we see a significant difference in the reactivity, we change the name. So in our very first case, instead of referring to that as primary, you'll see it referred to as primary, because it's still attached to one carbon, primary allylic. Okay? Allylic is referring to the red carbon atom, or the atom that we've got circled in red. That position is allylic. It is one bond away from a double bond, or a multiple bond for that matter. How about the last case? And that last case, if we look again at our red carbon, it is still one bond removed. Okay, and it still only has one carbon. So we'd be looking at primary, and we might call this allylic. Okay, but is there some other reactivity associated with this? That's a benzene ring. That double bond isn't sitting at just that position. There's resonance where it moves all the way around. So instead of referring to this as primary allylic, you'll see it referred to as primary benzylic. Okay. Again, that benzylic atom is the red carbon atom. Okay. We're not referring to the atoms on the ring, which brings up the next issue. If we look at that middle structure, okay, so this is why I should have changed the order on this. If we look at our benzylic, we say, oh, that one also reacts. So what about the middle one? We expect that one to react. Most people go, oh, benzene rings in both cases, it must react. What's the result? Not a reaction formed. Nothing happens. Okay? And the reason being, necessarily, is going to have to be because the carbocation that would form is highly unstable. If it's unstable, it can't form. Okay? I don't want to go into the details behind why it's unstable. Feel free to try and draw that out and evaluate that on your own. If you want to ask about it after class, we can. Okay? How do we classify that halide or that carbon or that halide? This one becomes a little bit weird. It's not really secondary because our primary, secondary, tertiary classification really only works when we're referring to an sp3 type atom. That carbon atom is sp2. Can't classify it based on our primary, secondary, tertiary classifications, so instead we refer to it as an sp2 carbon. Or a sp2 halide if we really wanted to, carbohalide, alkyl halide. I can use my words. Okay. So what this is really trying to put together is all of these big things, which then is going to take us to our final summary on this, which is nice there at the bottom. What we would expect is our tertiary, allylic, or benzylic to react the absolute fastest because it's tertiary and we have that resonance stabilization. Okay. Our secondary allylic should react a little bit slower than the tertiary because it's secondary, not tertiary. So it's losing some of that stability. We then typically see our primary allylic being, again, lower than our secondary, but roughly the same as our tertiary. Okay, so no double bonds at all. Why would our tertiary be roughly the same as the primary allylic? Why not put the tertiary all the way up at the top? What charge sits on this carbon in our tertiary? Positive. What charge sat on the carbon in our allylic or our benzylic structures? A half. We're seeing an actual drop in the charge due to resonance. In our primary, secondary, tertiary cases, we aren't physically dropping the charge. Okay? We are stabilizing it, but we don't significantly change the charge value itself. Okay? So when we're looking at our SN1, our primary allylic and our tertiaries roughly come out the same. Then we'll see our secondaries react, and then we will not see primary or zero area reactions with an SN1 mechanism. Okay? And that's because those carbocations are so unstable. Yeah, I said that right. Are so unstable that they just will not form. So our primary, our zero area, and our sp2s don't do any kind of reaction. So on a test, this is always a fun question. Let's take this as a middle structure here. On a test, I give you this option, put in the iodide, and we might see a variety of different things pop up as answers. And wow, let's get some super creative on this. Got a little wedge there. Let's drop in a third answer. The dash. Hopefully those are somewhat readable. And then our last answer would be NR, which would probably actually say no reaction. We wouldn't assume that you know what NR means. Okay. 3 of those answers all show some kind of substitution reaction occurs. So odds are it must have been a substitution. So if you don't know what's going on, what do you end up circling? One of those other answers. What's the correct one?
No reaction.
Absolutely no reaction occurs because that carbocation cannot form. Okay? What if it was left blank? Said provide the product?
The product would be the same as the reactant.
Okay, you could draw the product being the exact same as the reaction. I'd accept credit for that. I'd also accept credit for
Nothing.
no reaction. Wouldn't accept nothing, because nothing then means you may have left it blank. So I need something there to signify that you're saying no reaction occurs. Okay? Questions? So one of the, yeah?
What about, it's not on there, so I don't think it's important, but like, I remember reading vanillic, right? What is it?
Vanillic is another reference. So I'm just going to cross stuff out. If we crossed out this section of the benzene ring, so that's not there anymore, that halide is now referred to as vanillic. Vanillic just means that it's directly attached to an atom of the double bond. Okay. So you can call it sp2 or you can call it vanillic. sp2 is a little bit of a weird reference for it. Usually that works well enough, but vanillic is the official term.
Are we typically going to see this quite often, or?
It doesn't show up very often.
So that there's more.
Yeah. Okay. So when it comes to the SN1 mechanism, the one thing that you should be thinking every time you hear SN1 is, nope, cation, particularly the stability of the carbocation. Why might tertiary be useful? It's going to be one of our most stable things. It's going to allow for the SN1 reaction to occur. Okay? So if we're given just a sequence of substrates, you should be able to identify, yeah, that could do an SN1. That can't do an SN1. Okay, so you are responsible for being able to pick that information out. We do get some complications coming out of this. Those of you in the lab on Monday might remember that last one down here. We just talked about that resonance kind of complication. If there's resonance, we have to watch out for it because that can make a reaction actually go. Okay. Let's go back a little bit to our stereochemistry. What would we expect our product to be? So if we looked at the intermediate, or sorry, the SN1 mechanism, what's the first step that happens? Okay, we break our carbon-iodine bond first, and we would end up with, do the right number of carbons? Yeah, that species. Okay, and then we would go to our product, and we'd put the chlorine on there, right? Okay, most people pick that up. So we've done our substitution. Okay, that answer only gets you partial credit. Okay, why does that answer only get you partial credit?
The arrows.
If I just ask for the product, that answer only gets you partial credit, and it may not even get you half credit. Look back to your starting material. When we look at the starting material, do we have a stereocenter? Yes. Which means in the process of this reaction, we must watch out for that stereocenter potentially controlling the products of our reaction. So what do I mean by that? Look to your product. Do you have a stereocenter in the product? I have a CH3 and a CH2. Are those different from each other?
Yes.
Are those different from chlorine?
Yes.
Are those different from hydrogen? Do I have a stereocenter in the product? Yes. What should the stereocenter be? R or S? Okay. This is where we run into issues with our mechanism. So this is why we have to understand what is going on with the mechanism. And this is a favorite question for the ACS exam, because we can't, in the ACS, with multiple choice, have you draw out a mechanism. But we can absolutely say, what's the product of this reaction? If you don't understand the mechanism, you can very easily get the answer wrong. Okay? In the course of this reaction, we start with one structure, which happens to be what? 1, 2, 3, what do we have? The R? I think I did that right. We have the R enantiomer. When we get to the product, we haven't specified the wedge and the dash. We just drew on where the chlorine was, but we didn't specify if it was wedged or dashed or what was going on with that. Okay? The only way we would be able to do that is by understanding the mechanism. What happens in the very first step of the mechanism to our stereo center? It disappears. It is no longer present. What we're left with is a carbocation. Okay, so this goes now back all the way. We talked about orbital diagrams and what our orbitals were and hybridizations, and everybody's like, oh, I'll never need to know that again. Sorry. What's the hybridization of that carbon? sp2, which means there's one p orbital left over. What does a p orbital look like? Dumbbell. Where are the dumbbells on that p orbital? If we assume this drawing is drawn three-dimensionally correct.
Towards us?
One dumbbell is coming at you, one dumbbell is going away. Why is that important? What can you put into a lobe of the dumbbell? Electrons from your nucleophile. Which means if we're going to add our mechanistic arrows to this, what did I say was the nucleophile? Chloride. My chloride can attack from the bottom of my structure, but it can also attack from the top of the structure. What does that give us as far as the stereo center? We get both forms coming out of that reaction. Okay, so what we end up with at the end is a mixture of both the R and the S. How would you specify that as far as predicting your products?
Just like that.
Okay, one option, write it out like that, R and S.
Draw both products.
Okay, draw both products. Draw one with the wedge, and then I think, well, since I'm going to make you do it. And then draw one with the dash.
But we can get away with just saying R and S.
And you can get away, if you show one of them and say, I get both the R and S forms, yes.
Awesome.
To be a little bit careful on that, what happens if there's another stereo center in this?
It's to specify for each form.
Yeah.
Okay. I can't just say R and S anymore because that other one isn't going to change.
You actually name it. and
Okay.
mark it.
So we could go through and name it. Okay. Or what we could go through and do, okay, we could try and say plus an enantiomer. Well, that still doesn't work either. Okay. So what we want to do is make sure that you specify that information as best as possible. You may be able to write down plus an enantiomer as long as you don't have another stereo center. You might have to draw both out. You could also get away with probably saying plus and minus. Why plus and minus? It goes back to their optical activity. They'll rotate lights optical or different directions. So we all end up with both. Okay. If this was our reaction, okay, this is another good favorite question on this that goes all the way back to our stereochemistry. I don't ask you to predict the products. I say, here we go, this reaction occurs. Okay. We take our, what is that, iodopentane, or 2-iodopentane, or 2-iodopentane, react it with chloride, and I evaluate the product. Does it have optical activity?
Did it come out in equal amounts?
Okay. If this strictly separates according to the SN1 mechanism, and we really do form that carbocation first, okay, then it moves forward. We're looking at a 50-50 mix. Complete random odds of top versus bottom, and our optical activity is 0. Okay? That's theoretical. In actual experiments, what ends up happening?
One gets made than the other.
We get one slightly more than the other. Okay, why?
Because statistics is dumb.
No, it doesn't have to do with statistics. So if it's just strictly statistics, we're close enough to 50-50 that we get virtually no optical activity. Okay. If you have a stereo center in your reaction, that stereo center will affect your product. Doesn't have to do anything with the mechanism. Okay, so I can take a random reaction, okay, and I throw a random stereochemical product in, or material in there. Doesn't do anything with the mechanism itself. Doesn't bond anything, doesn't act as an intermediate, doesn't do any catalysts. It will change the composition of our products. So if we start with R, we will see a slight favoring of the S just due to kind of steric considerations and things getting in the way. Okay? Even though in the SN1 mechanism, in theory, we completely split that and we get a 50-50 mixture. Okay? So as far as test questions go, we'll run based on theory. Okay? Realize in experiment, it doesn't always work out perfectly.
So
Yes.
in that case, if you're going to ask about the optical activity of something like this, then you would expect
I want
not
the
to see any.
theory answer,
So
is what I'm going to be
you
looking
would
for.
expect not to see any.
I would expect to not see any optical activity. Okay? Questions? Yeah.
Yeah. For the, you did the top bottom, didn't we say the dumbbells are pointing towards, like,
So one's coming at you and one's going away. So you could say one comes in from the front, one comes in from the back.
okay, right. So
That's
bottom-
effectively the same thing as top bottom. Top bottom would be if I drew it. You're still going to get the opposite result. Sorry, I talked over you. Did you get your answer?
Yeah.
Okay. Okay, so our summary from that, if we start with stereochemistry, then we lose it in our products. Okay, so we will end up with a not optically pure product. Okay, and that's where we would get kind of strict with our definitions. It's not optically pure. Very likely it will be optically inactive. Okay, so that, not optically pure is our experimental observation. Not optically active, optically inactive, same thing, would be our theoretical. Okay? Other complications. We can deal with, oh, we already did resonance. Shucks. I should have drawn a better structure. Oh, I created a new slide. Never mind, sorry. If we look at our intermediate in an SN1 reaction with this case, what do we end up with? What kind of carbocation? I'll accept two answers on this. Primary is one of them. What's the other answer? Primary allylic. If we assumed it was just primary, would we expect this reaction to work?
No.
No, we'd say no reaction. Does this reaction actually work? Yes, it does. Why? There's a resonance stabilization. Let me show that in a different color. And we end up with this carbocation. Okay. So we should expect a reaction because we have that resonance stabilization. Okay. And with the allylic one, it didn't matter which resonance structure I looked at. I got the exact same amount of products because they were both the same. But if we go through and now look to see what happens after our nucleophile attaches, do we get the same product? Where does our nucleophile attack? The positive charge, where the or it's not where the bromine is, it's where the bromine was. So it's going towards the positive charge. So in one case, I expect this product. What about the other resonance structure? I expect that product. Are those products the same? No. Uh-oh. What does that mean we're going to have to deal with? We have, they aren't stereoisomers. These are actually structural isomers. Okay. If I ask you to provide the major product, which is your major product? Right or left? So theoretically both, which is why I said major product. So one of these will show up to a greater concentration than the other. That's now going to become our major product. Which of these is our major product?
On the left, it's easier to attach to the end than in the middle of everything.
Yeah, because of the.
I guess it's that one.
It's the rightmost one. Does steric hindrance matter in an SN1 mechanism? No. What is the only thing you should be thinking about in the SN1 mechanism? The stability of the carbocation. What kind of carbocation do we have on the left? We'll come back to your question. On the left,
Tertiary allylic?
Primary allylic.
primary allylic.
Oh, on the left side.
I kept thinking I was saying it backward.
No.
On our right
Tertiary.
is our tertiary allylic. Which of those two is more stable? The tertiary allylic. Which one's going to lead to our final product? The tertiary allylic. So what we end up with is our tertiary allylic giving us our major product. The other one would be a minor product. Okay? Focus on the stability of the carbocation. We do not care about sterics. Okay. Question? Or are you frantically still writing that?
Talking about the product, right?
The product, yeah. Bobby? Did you still have a question?
Yeah.
Okay. So this is one of our complications within resonance. Resonance not only helps us actually push the SN1 mechanism, but it's also going to change what products that you potentially get out of it, depending on what your structure looks like. Okay. How would you know which structure to use? Draw it and evaluate its stability. If you don't ever draw it, you never see that this other one is a possible product, and what you end up giving for the answer is the wrong answer. Okay? Questions about that? Mm-hmm.
It's unstable. How come it's still
The
form a product?
primary allylic is stable enough to form.
It can form a product.
Okay? It can form the product. So now what we've got to decide is we look at our resonance and then we go through and say, okay, between our resonance contributors, which one is most likely to generate our product? The tertiary allylic or our primary allylic? Back to that previous slide, which one was more stable? The tertiary allylic, that one's going to generate our product to the largest amount. All right? Now, everybody's favorite, we're going to talk about rearrangements. So before we move into that, because that one is a beast, no more questions on resonance. You guys okay with that? Okay. So summary first on our resonance/rearrangements. If the structure can make a more stable carbocation, then it will, period. Okay? That means within the SN1 mechanism, resonance and rearrangements can mess with your product distributions. So you must evaluate both resonance and this potential for rearrangements. Okay? So let's take a look at our rearrangements. This is an entirely brand new slide. I realized that I didn't give a very good structure for that previous one, so let's draw a new one. I want to do this in black ink. And I'm going to tell you right off the bat, so we don't even have to wonder about whether it's SN1 or SN2. SN1 mechanism, give me the SN1 product. Okay? So Monday lab will have a little bit of a cheating effect on this. Let's give you 30 seconds to predict what the product looks like. There's our product. Huh. That's a bit weird. What's going on with that? We have the same number of carbons, but what happened with our nucleophile?
Looks like it replaced the hydrogen.
It almost looks like it replaced a hydrogen. Our nucleophile, for some reason, went to that other carbon. It didn't go to the one where our halogen left. Okay, so let's work through the mechanism. First step of our mechanism, what happens? The leaving group leaves. So our bromine takes the electrons, and we end up with our carbocation. What kind of carbocation do we have there? Secondary. Is secondary particularly stable? No, it's at least stable enough to form. It is still part of our SN1 groupings for substrate structure, but it's really, really unstable. Okay? So this is where rearrangements come in. So what we can go through and do is try and find a source of electrons close to that carbocation, because it's still going to take a little while for that nucleophile to come in. So we're going to look for an electron source somewhere close to that carbocation. Where's the closest source of electrons to the carbocation? The bonds immediately next to it. So we could try and take the electrons out of that bond and put it on that carbon, but then what happens to the other carbon? We've lost that bond, and the other carbon is now positively charged. Okay? We could also go through a whole separate argument on that, and that those electrons can't even go in to stabilize the positive charge. What we end up forming is a carbene, okay, which we won't talk about this semester. That's a whole separate issue. Okay? So what it's going to do is not go to those bonds, but then go to the atoms further out. Okay? And we can't really go to those atoms, those carbon atoms that are attached out there, because there's nothing it can really pull from there either. So it's going to go out one more bond. Okay? And we're going to look at those electrons. So what we're talking about is the electrons in these highlighted red bonds. And what we would attempt to do is take the electrons in that bond and the atom that it's bound to and move those towards the carbocation. Okay? So let's pick one of those, which I'll now recolor as blue. Let's take those electrons and that atom and let's put that towards our carbocation. You'll typically see something written along those lines. Notice where the electrons started. Where did they start? Started on the atom, not in the bond. So what we're saying by that is that we took the atom and the electrons and we put them on that carbon. So what happened to that tail carbon? It now lost electrons, and our positive charge is now on the end. What kind of carbocation do I have here? Primary. Is that a good thing to do? No, that actually was a horrible thing to do. Okay? So does that happen? No. Sorry for those of you that copied that. And then as far as frantically erasing, I would actually recommend that you do not frantically erase. You write down that this doesn't work. Okay? Because a lot of what we're dealing with within organic chemistry is draw it and go, oh, that didn't work. By erasing it, what you've done, particularly with your notes, is we went through a process that said this fails. You've now erased that information from your notes, which also means you've erased that information from your head. So when it comes back to an exam, and I say, oh, this happens, you go, oh, sure, why not? Okay? Failure is actually a good thing. A failed experiment means that did not work. We need to change our conditions. Same thing is happening when we look at our mechanisms. A failed mechanism means we need to go back and adjust and not do the same thing again. If you erase everything, you run the tendency of repeating your exact same mistakes. Okay, so having a track record of that is actually a good thing. Okay? So what we can now go through and do is evaluate any of those other three bonds. Okay, any one you want, I would recommend that you test all three of those. Okay, we're only going to test one. That one that we're going to test is going to be to that hydrogen. We'll do the same thing, except this time I want to make sure that I'm accenting the fact that I'm taking that hydrogen atom. Okay, this is a non-standard thing to do. So we'll start our arrow at our hydrogen, but instead of just looping it down to our positive charge, I'm going to add a little curly Q in it. That curly Q is my way for me to say something weird is going on here. And that something weird is that I'm moving the hydrogen atom with it. What's our result?
Tertiary.
The hydrogen is now at our secondary carbon, and what happened to that other place? It lost electrons. It's now a new carbocation. That carbocation is tertiary. Is that more stable than the secondary?
Yes.
Yes. That means this step occurs. What kind of step is this? It's a rearrangement. We rearranged where the atoms were located to generate a more stable structure. Okay? We're only allowed to do this if we make a stable structure. So we can't go, I'm going to do 5 rearrangements to get to a stable structure. If that fourth, third, second, and first rearrangement don't generate a stable structure, we don't have it to move on to the next one. Okay? So when we're looking at our rearrangements, very, very typically, you're only looking at one rearrangement, and that's it. Okay? Now that I have the tertiary carbocation and that it is more stable, what can happen? Now my chloride nucleophile can come in and attack, and I end up with my product. Okay. This is a massive complication of SN1 reactions. Okay. So if we're going to try to run a reaction, we want to make sure that we're aware that rearrangements are possible under the SN1 conditions, and if I don't want a rearrangement to occur, I should not choose those conditions. Okay. Questions about the rearrangement? Okay.
So not choose those conditions, meaning not choose that structure.
So it could be as much as that structure, but ultimately the biggest thing is not going to be that mechanism.
Okay.
Okay. So I would want to change the mechanism. Is there another type of substitution reaction that I could do? I could run an SN2 reaction. And we'll look at the SN2, and one of the things that's nice about the SN2, no rearrangements. Why? There's no carbocation. So any mechanism that shows a carbocation, watch out for those rearrangements. Okay? I did download this real quickly from Wikipedia, so don't blame me on the image quality on it. But what we're seeing here is a sequence of steps, so it's a fairly complex reaction. But what we're evaluating is actually a rearrangement. So in that first step, what changed? What type of reaction happened in that first step? We have an acid-base reaction. What happened in the second step? Did it rearrange in the second step? So this arrow right here. It's not really hydrolysis. Based on the mechanism information that we've got, we're starting to do a substitution. By starting, we're looking at the first step of an SN1 mechanism. We're looking at the leaving group leaving, okay, and the formation of our carbocation, which we saw in an SN1 mechanism as our first step. Okay. It's a little bit weird because we aren't doing strictly a substitution in this case. We're doing some other chemistry. But with the knowledge that you have, that's how you would classify that. That would be our SN1 first step. What happens in our second step? Or sorry, third step? Now we have the rearrangement. We started at a tertiary carbocation. That's actually really stable. So why would it rearrange? Well, do the rearrangement. What's the result? We still have a tertiary carbocation, except we have that oxygen instead of a carbon. What's special about that oxygen? Lone pair electrons that it can actually share via resonance. So it is a resonance-stabilized carbocation. That means that rearrangement step is actually a successful one, and that's where our rearrangement ends up occurring. So anytime you see that carbocation, you've got to watch out for that potential for rearrangement and look at that new rearranged product. Can we make that carbocation more stable than the previous one? In this case, we can. This particular rearrangement is known as the pinnacle rearrangement or the pinnacolone rearrangement because the product in it is pinnacolone.
Should we lose the hydrogen off the oxygen?
You will eventually lose the hydrogen off the oxygen because you end up forming the double bond. Yeah, they didn't mechanistically show that very well. Officially, you would have another step there. We can cheat sometimes with mechanisms, and our cheating step would be make that arrow a little bit longer. We're taking the electrons away from the hydrogen bond and putting them into the pi bond. So we could now say,
Step with the oxygen being a plus.
yeah. Okay. So it's just, all I'm trying to show here is that we do see rearrangements. This just happens to be one of the more famous rearrangement reactions. Okay. Within our SN1, we've got kind of our summary here. Primary thing you should be concerned about is the stability of the carbocation, which is dealing with our substrate. So we've got all the things that we've discussed. We've got our substrate, We need a good leaving group because it has to leave. The nucleophile we really don't care about. So if we don't have to care about it, it might as well be weak. Because if we make it strong, that's potentially more dangerous. So we'll use weak nucleophiles when looking at the SN1. The solvent will be polar protic. The reason it's going to be polar protic, our primary thing to be concerned about in the SN1 mechanism was what? The stability of the carbocation. Why would a polar protic solvent work best to stabilize the carbocation? If we look at our classic example of a protic solvent, we've got water. The one that we evaluated was the partial positive messing with our nucleophile. But how did it become partially positive? The oxygen took electrons away, generating a partial negative. That partial negative can stabilize the carbocation, allowing it to react or actually form. Okay? So in an SN1 mechanism, we want a polar protic solvent because that one's going to give us the largest partial negative to stabilize our intermediate, or our carbocation intermediate. Okay? When it comes to stereochemistry, we're going to have a loss of stereochemistry. And then with our complications, you're going to have to watch out for rearrangements and resonance. Both of those can potentially bite you if you aren't looking for them. Questions about the SN1? Okay. I'm going to give you 2.5 minutes. So if you've got questions, raise your hand and ask. I'm only giving you 2.5 because I want to get through the SN2. So you know I'm such a fan of color coding. So the first one, you should end up with 2 products because it's an SN1 reaction. That second one, what we can do is look across the reaction and say what changed. Well, what changed was we had an S and 2 carbons. So at very least that needs to show up as a reactant. How many bonds should sulfur have? 2 bonds. So one of the natural instincts for people to say is, well, that needs to be a nucleophile, so let's make it negative. What's the issue with that? That nucleophile is now strong. Do we want a strong nucleophile in an SN1 reaction? No. So I need a temporary bond on there, something that's easy to pop off of that sulfur that's positively charged. What might that be? Hydrogen. The answer in that case is actually going to be that guy. Okay? So you have to be aware of what those conditions were. If we put it on as S-, we'll get a different product, okay, which we'll see in the SN2. The third one, kind of a difficult one to deal with. We've got OH-, sodium hydroxide, also known as a base. So before we start immediately jumping into a substitution reaction, we need to evaluate what's going to happen. What does a negative want to do? Grab a positive. Where's there a positive atom? The hydrogen is positive and also the carbon. Would we expect a substitution reaction happening at our carbon? No, because that is a vinylic or sp2 carbon, which does not react in a substitution reaction. Which means we don't have a positive carbon. The only thing that we have as positive is the hydrogen that's attached to the oxygen. So that very first step of the reaction was what? An acid-base reaction. Removed the hydrogen from our oxygen, and what we end up with is what's known as phenoxide. What is special about that intermediate product? It is very negatively charged. It could act as a base. Okay, so we have a base or a nucleophile. So then we move to step 2. And in step 2, what do we bring in? We've got carbon and bromine, potentially hydrogens in there as well. Which of those is the most positive? For hydrogen to be positive, what does it need to be attached to? An electronegative element. Where's our hydrogens attached to in structure number 2? Carbons. Do we have any positive hydrogens? No. What do we have that's positive? The carbon. So what does our intermediate structure react as? A nucleophile to attack our carbon, and we end up with our final product. Tricky. You're still officially responsible for your acid-base reactions. You need to be able to string them in there, all right, if need be. So when you go through and do a reaction, positive and negative, find the most positive, find the most negative. Do not force a reaction to occur if you don't have that information. Yeah.
In the product, would it not have that extra line on it? Doesn't, or,
How many carbons are in number 2?
oh, no, I meant,
2
sorry.
carbons.
Yeah.
Yeah, it definitely looks like it's got more
Yeah.
bonds, but you got to watch out for your carbons. That was actually an odd example, because that's really an SN2 one, but beside the point. Last one. Why do we end up with the product that we do?
Tertiary.
We have a resonance intermediate that puts us to a tertiary carbocation, which puts the cyanide attacking at that position. One of the things to watch out for, it is very, very, very common for people to include that bond as a carbon at the end. So drawing something like this, let's highlight it as a purple. Okay. On its own, it really doesn't look that different. It doesn't look that bad. Okay. One of the things that you should be aware of and start to do, at least when working with the homework, is count your carbons. A carbon is at every single point. If we counted that purple line as an extra bond, we have an extra carbon, which means our answer can't be right. Go back through and evaluate and make sure that you don't accidentally bring in a new carbon. Very easy to do. It happens all the time. It was probably one of my least favorite exam questions. I did that by accident, couldn't figure out what was wrong with the reaction, so I couldn't get to the product. Okay. So those are our SN1. Is that a question? What's up?
Why was there mention HS?
What mechanism are we running under? What's the question asked? Predict the products of what type of reactions? SN1. And in SN1 reaction, what do we want our nucleophile to be? It needs to be weak. If we don't put that hydrogen on there, it's negatively charged. It's now a strong nucleophile. Okay. If we put on any other type of atom, we neutralize the reactivity of that sulfur because we can't take that other atom off as easily as our hydrogens. Okay. SN2 reactions. So in the SN2 reaction, you remember all the way back to whenever we talked about it, I think last week, what's going to happen is we're going to break our leaving group bond, our carbon leaving group bond, at the same time that we form our carbon nucleophile bond. So if we start with our standard substrate, and we want to show that bond breaking. How do we show that bond breaking? We're going to take our electrons that are in that bond and we're going to move them to the leaving group. But we're saying that we are forming the nucleophile bond at the exact same instant, which means I also need to draw in my nucleophile. What's the characteristic of a nucleophile? It's got electrons, so I could tag a lone pair on it. We're going to have that lone pair share its electrons with that carbon at the exact same instant. In the process of doing so, what I end up with, my nucleophile below and my leaving group having left with its lone pair of electrons. Okay. Why did I show the nucleophile attack from the bottom? Why is it bad to show the nucleophile attack from up here? The leaving group is leaving with electrons. The nucleophile is bringing electrons in. What happens when those two electrons get near each other? They repel. So when we're looking at the SN2 mechanism, what we are primarily concerned about is minimizing steric hindrance. Steric hindrance is just talking about electron-electron repulsion. We don't want electrons getting near each other. Okay? So when we look at our mechanism, you'll notice we get pretty much the same thing. I did add an extra little step here. What's that extra little step showing? It's showing the transition state. Right? That is not part of the mechanism. Why is it not part of the mechanism?
Happens simultaneously.
Sort of. If I ask you for the mechanism, the only thing that I expect to see for the SN2 reaction would be just that top section. Why show the intermediate? It's helping us see the inversion of configuration, which is going to be one of our complications of the SN2. We get a change in stereochemistry. Right? So that transition state allows us to see that change, how the bond is forming and how the bond is breaking. You'll notice that they are on complete opposite sides of the structure. And that's because of that steric interaction. We want to minimize that as much as possible. Okay? Just like we did with the SN1, we're going to be concerned about the speed of the reaction. Okay? So which step is our slow step? There's only one step, so that step, by definition, must be the slow step. How many species are involved in that slow step? Two, the nucleophile and the substrate, which means this reaction is a second-order reaction, also known as bimolecular. Why do we refer to it as SN2? Because it is a nucleophilic substitution reaction that involves two species in our rate-limiting step. Right? That's where our SN2 term comes from. So our rate is going to be equal to our rate constant times the concentration of our substrate times the concentration of our nucleophile. You may or may not have heard of this when you took 152 and you looked at these rates, and even with your equilibrium constant. Is it really a concentration that shows up in these? No. It's not a concentration that strictly shows up. It is something that is directly proportional to the concentration, and in nearly all cases we can get away with calling it concentration. What is it supposed to be? It's the activity of that particular species. Okay, what do we mean? If I make that nucleophile more reactive, what we're doing is changing its activity. If I increase its activity, what happens to the rate of the reaction? It gets much faster. Okay, so we aren't strictly changing the concentration between our SN1 and our SN2. We're changing the activity of these species. So if our nucleophile becomes stronger, that's going to help our SN2 reaction because it will go faster. If our substrate becomes more reactive, it's going to go faster. What's going to determine that reactivity? The nucleophile one is easy to see. The substrate one might be a little bit more difficult. We're looking at a backside attack. What's on the backside of that leaving group bond? Okay, so if it was in its original state, this would be tetrahedral, right, with these aimed downwards. What's on the backside of that bond? Whatever those atoms are. If those atoms have a lot of electrons, what's going to happen when that nucleophile gets near it? It repels away. So we get a steric hindrance that prevents the SN2 reaction from working because the backside is blocked. Okay? So when we're looking at the SN2, we are only concerned about sterics and what's happening on the backside of that bond. So what atoms would I prefer to have on the backside of that bond? Okay? It can't be none because it's carbon, but that's not a bad idea. What's as close to no protons, no electrons that we can get?
Hydrogen.
Hydrogen. The best substrate for an SN2 reaction is where we have hydrogens on the backside. If we make all three of those atoms hydrogen, what type of substrate do we have? We have a methyl, way to get fancy on me, or a zeroary substrate because there's no carbons attached. When we start to add more carbons, what are we also adding? More electrons. Those electrons increase the steric hindrance and we can prevent that reaction from occurring. Which means when we evaluate our substrate, which substrate's going to react the fastest? Primary, secondary, or tertiary? Our primary will react faster than our secondary, faster than our tertiary. Our tertiary is so sterically hindered that just like we did for the SN1, we can eliminate that as a possible option. We could also throw on our zero area, reacting even fastest. So when we're looking at our substrate structure, we're looking for zero area primary or secondary. Anybody see any issues with this? If I give you a secondary substrate, which mechanism does it go? SN1 or SN2? It can go in either one. So how would we decide? Look to the other of those four different things. Substrate. Leaving group is going to be the same for both, so we don't have to worry about our leaving group. So substrate, nucleophile strength, and solvent. Our nucleophile strength for the SN2 needs to be strong. What's going to make it strong? A negative charge. So if you see a secondary substrate, we have no idea what mechanism it is. Look to the substrate. Or sorry, what's the other thing? Nucleophile. If the nucleophile is negatively charged, we're looking at an SN2 reaction. What if we don't give you the nucleophile?
Solvent.
Now we've got to look to the solvent. Well, how is the solvent going to impact this? There's no carbocation to stabilize.
So we want,
What we are looking for is a strong nucleophile. That is the most reactive thing in our rate law. Just like when we went back to the SN1, the most reactive thing was our carbocation. That was what we were primarily concerned about. And with the carbocation, what did we want? Most positive or least positive? Least positive. So we used a solvent to make that cation least positive. When we look at our SN2, what's our most reactive thing? The nucleophile. Do we want our nucleophile to be more negative or less negative? More negative. So what solvent should we put in there? Something that is not going to change that negative charge. So it should ideally be nonpolar. However, our nucleophile is charged. Is a nonpolar solvent going to dissolve it? No. If it never gets dissolved, it can never react. So it will still need to be a polar solvent to dissolve our nucleophile, but it does not, we don't want to push all the way up to that protic situation because that weakens it. So we end up with a polar aprotic solvent. All right? Complications. When we look at the complications of the SN2, you've seen this reaction before. I threw this at you and said predict the products for the SN1. We ended up with 2 products. How many products do we end up with for the SN2?
1.
Only end up with 1. What is that one product? Where does the sorry, I shouldn't be iodide. Where should the chloride be? If it's where the iodide was, this would be our product. It must come in from the backside. So if our iodide is coming at us, the chloride must be going away. So we would show it as the dash. I noticed that you were pointing downwards. Iodide's pointed up, chloride's pointed down, right? That would be the complete opposite. Remember, this is a 3-dimensional structure. In the process of doing that conversion, our orientation or our view on the structure slightly changes. We almost always rotate it back to the position that our carbons are all in the same plane. Okay? If you do just the strict backside attack, you would notice that you won't have all the carbons in the same plane and it gets a weird drawing. Okay? There's another way I could have drawn this product. What should the chloride be now?
towards it.
Why?
Because you flipped it right.
You just flip the structure. Okay? You can still do that. Just for future reference when it comes to the exam. That does kind of irritate me. Because you've now flipped the structure. So you drew the correct answer and then you flipped it just to confuse me. If you get marked off, just let me know and I'll give you the points back. I do try and watch for that whenever you're drawing products. And I also try and pick structures where it's not going to be your natural instinct to flip it. Okay? So it makes it easier to grade. So what does that mean to our stereochemistry? We started with which stereoisomer? We started with R. What did we end up with? S. Interesting. What happens in the SN2 reaction? the stereochemistry changes. We go through an inversion. Will it always change? Not necessarily. It depends on what the nucleophile is and what all the other groups are. Probably 5% of the time, you will get a stereochemistry change. You will go from R to S. I have to actually work hard to make a question where you don't see inversion. Okay? Realize you're getting that backside attack. The natural tendency is to get an inversion of stereochemistry. You should still officially determine if it's R or S when you look at your products, just to make sure it actually inverted. That process is known technically as a Walden inversion. Do we have to worry about resonance or rearrangements? When did we worry about resonance and rearrangements? When you have a carbocation. Is there a carbocation in the SN1 or in the SN2 mechanism? No. So this is a nice thing about the SN2 reaction. Since there is no carbocation, there are no rearrangements, there are no resonance issues, okay, which makes things even better for us for a couple reasons. Synthetically, it's going to be preferable because I don't have to worry about all these other weird things happening within the reaction. Take it a step further and look at the stereochemistry. When we look at the stereochemistry in the product of the SN1, how many products did we get? 2. In the SN2 reaction, how many products do we get? 1. So if I'm going to run a reaction, which reaction or which mechanism is going to work the best for me? Probably the SN2, because I'm only going to make 1 product. I don't have to worry about a secondary effect. Okay? So the SN2 tends to be a much more preferable reaction. We do have to be careful with that because we do change the stereochemistry whenever we go through and do those reactions. So you might have to cycle reactions to get the stereochemistry appropriate. Okay? Within our SN2 summary, so we've got a summary reaction. Again, we're showing the transition state intermediate. How do we know that's the transition state? Number 1, we've got the bracket on it, but more importantly, it's got the double dagger. The double daggers are universal symbol for our transition state. All right? So our conditions to be concerned about, when we look at the substrate, we want the smallest substrate possible, which means our primary before our secondary, okay? Our zero area before our primary. The leaving group, we still need a good leaving group. Substitution, we need that thing to come off. Okay? Our nucleophile needs to be strong because it has to force the leaving group to leave. It's what's causing it to get kicked off the structure. So our nucleophile has to come in very, very strong to help for that process. So if you're going to look for a nucleophile strength, what's the first thing you should evaluate? Not just electrons, but negative charge. If you have that negative charge, you have a strong nucleophile, which means probably doing the SN2 mechanism. Okay? What if I give you a negatively charged species and I say do an SN1 reaction? Which one should you do, SN1 or SN2? SN1. Why? I told you to do the SN1. Okay? If I tell you to do it, don't make it more complicated. Just do what I tell you to do. Okay? Our solvent needs to be polar aprotic. It still needs to be polar to dissolve everything, but we don't want it to be so polar that it weakens the strength of our nucleophile. We're done at 30 or 40? 30. Dang it. Stereochemistry, it's going to, if we start with it, we're going to get an inversion of stereochemistry. Okay? Benefit of our SN2, no rearrangements. Okay? And because I actually want to push through some more stuff, I want to get through some of the summaries, we're going to sort of skip this. If we take a look at that first reaction and we ran it under an SN1 mechanism, we would probably get number 2. So this would be our SN1 product. Under the SN2 reaction, do we get a rearrangement? No. Nope. And an SN2 reaction, we don't have to worry about the rearrangement, and we get the product that we would standard expect. The next reaction on the right, you'll notice, is very, very similar to what we just looked at for the SN1. What's the big difference? There's only 1 product, which means I went under SN2 conditions, which means my nucleophile needs to be strong. Now I can put in the negative charge. Okay? For that next one, I said I wasn't going to do this, but we're doing it anyway, just because I started. We'd have that wedge over there where nothing happened. What's going to be at our other carbon? That carbon needs, sorry, I meant to do that in red. Our other carbon needs to have some partial positive associated with it so that that nucleophile can attack. Will it be formally positive? No, because that's an SN1 reaction. We're only ending up with one product. So it's got to be SN2, and it needs to be a good leaving group. What's my good leaving group? Any one of our halogens except for our fluoride. Typically I would show bromine. Should that bromine be wedged or dashed? Dashed because our product is wedged. We have an inversion of stereochemistry. That last one we've talked about a million times. I'm not going to draw that. All right? So, tail end of chapter 7 is now trying to decide which reaction is happening. Is it an SN1 or is it an SN2? This slide summarizes pretty much everything that you could go through and see. I try to highlight things according to different patterns. When we're looking at our mechanisms, that very first line is where I would focus all my attention. Everything underneath that first line is derived from that first line. Okay? Carbocation stability is the most important thing in both, or in our SN1. Okay? That's going to depend on everything that follows underneath. We want the tertiary substrate because most stable carbocation. In our SN2, we want minimal steric hindrance, which means what substrate reacts the best? Our methyl or our zero area, faster than our primary. Okay? So this summarizes pretty much everything, including your rates. Okay? As far as how you should go through and process a problem, start with the substrate structure, then move to the nucleophile, and then if you really have to dig for it, then you can jump into the solvent. Okay? Why avoid the solvent for the last? What's the primary reason we have a solvent? To dissolve stuff. It's only when we move into that secondary reason behind why we use a solvent, which means it's less important than everything else. Okay? Keywords, literally I promise it's just 2 slides and I only need 30 seconds. There's this thing called the Hammond postulate. What that's saying is that the transition state for your reaction is closest to the reactant or product that is closer in energy to it. Sounds kind of confusing, but if we shift to an energy diagram, we take a look at an endothermic reaction. Where would we expect our transition state to be closest to in energy? Our reactants or our products? Products, because it's closer in energy. If I change the energy of products, I'm going to see a significant change in my transition state. Okay? Because the transition state energy is dependent on my products. If I move to an exothermic reaction, it's closer to the reactant energy. If I end up with 2 possible products, true, I will have a difference in energy there, but will that affect my transition state or the speed of the reaction? No, because what determines our transition state in the exothermic reaction? The energy of the reactants. That's ultimately all Hammond postulate is really trying to talk about. Okay? Very last thing, SN1 is on the left, SN2 is on the right for our energy diagrams. You should be able to pick that up and figure out why that is. But I will stop there. We did have that conversation about me continuing to lecture, right? Should I do that? Another 20 minutes? So there's no traffic?
You don't want lunch before that?